welcome to technical session number 18. Where we're going to start taking our first foray into the networking world. We're going to start learning a little bit about the types of networks we experience from time to time. We're going to be talking about our LANs, our WANs, our PANs, our MANs, our CANs, all that kind of stuff. We're going to be talking about topologies, which is essentially just a fancy way of saying how the network is set up physically. We're going to be talking about network devices, starting to delve a little bit into the OSI layers. And lastly, we're going to kind of do a little bit of a review on some network connectors. We've seen some of them before, like the BNC connectors and the F-type connectors, the RJ45s. But we're also going to talk a little bit about fiber optics. So we're going to dive in just a little bit on this. Main objectives, going to define network and give some examples of networks. Identify the devices used in a network. Identify types of network cables and connectors. And then recognize the most common network tools that we use on a regular basis in the industry. Maintain our growth mindset. If this is our first exposure, don't expect that we're going to be experts right out of the gate. There is no expectation that we're going to be an expert first time we see something. But through time and exposure and practice, we can become extremely proficient and eventually an expert, right? Also, adaptability. There's going to be a lot of terms thrown at us today. But again, time, exposure, and practice. And we will become very proficient at it. And in short order, we'll be using these acronyms and stuff without even realizing it in general conversation. So let's start within a basic sense here. What exactly is a network definitionally? Tomas, can you read that for us, please?
A network links computers for communicating and sharing information and resources. A network must provide connections, communications, and services.
Very good, thank you. So it's the linking of multiple computers together, could just be two, for the purposes of communicating and sharing information and resources. Very basic sense, that's all a network is. What are the primary components of a network? So we break it down in some very basic sense. Let's see here, Rahel, can you please read what a client is for us?
Client, device the end user uses to access the network. Example, PC, laptop, smartphone.
Excellent. So in essence, we're all clients, right? We are on our computers connecting to a network. So our computers are clients to said networks, right? Nessanet, can you please let us know what a server is?
Server device that serve up resource to a network, example, email, web, file, proxy.
Excellent. So there's many different types of servers. A server is a very, very basic term, but there's a dozen different types of servers. We will get into them, but what they do is provide resources. They serve up things for the network to utilize in a very, very general sense. Now, how are we able to communicate? Jamari, can you please let us know what a network device is? All right, Emily, can you please let us know what a network device is?
Do you want me to read it or?
Yes, please.
Okay. Network devices create the network. Example, switches, routers, access points.
Excellent. So they essentially facilitate the means of communication. Now we can plug one computer directly into another and have those talk. But what happens when we get up to like 10 computers? We have to have devices that help facilitate this communication and route it and manage it for us. Because it would get pretty bad if you have 100 computers in the office and you had to connect all 100 computers to each other through cables. Hint, that's called a mesh network. And it gets really expensive, really fast, and really difficult to maintain. And lastly, let's see, Stephen, what is media?
Yeah, media is via to interconnect devices. It could be wired or wireless. An example could include copper cable, fiber optics, Wi-Fi.
Excellent. So what media are you transmitting that information on? Over the air, copper wire, which would encompass coaxial cable as well as UTP and STP cables, or fiber optic utilizing light. What type of media are you using to connect to these network devices, which then connects you to the greater network? So in essence, these are our 4 basic components of any network. So now we need to talk about what are called physical topologies. We already kind of gave you a brief look into the star topology. So let's go back to the beginning. One of the oldest types of networks that you will see is called a bus. Old joke used to be in the networking world is I'm riding the bus. And what it is a straight line cable essentially that comes through, and then each computer is connected to that central trunk line essentially. This was originally done on coaxial cables. And if you've ever heard somebody in the office say, or an IT person say, I need to add a drop or drop a line, this actually can't, this term comes from physically them having to go into the ceiling. They would put like a spike into the actual bus line and then physically drop a cable down to the desk that would have a connector that you would connect to the computer. So that is particularly where that term comes from. Again, runs on coax, but it is extremely vulnerable and is extremely slow because the communications have to kind of go up and down this communication line.
They would put like a physical like metal spike into the cable?
Yeah, it's called a vampiric connector. So, because it was a coaxial cable, what it was is it would go around the coaxial and then they would screw in a spike that would touch the copper, and that would allow you to tap into the communications. Literally
it's like tapping a
tap
tree
in.
trunk.
Yeah, exactly.
Wow.
Love that
Okay.
name though, vampire, biting into the line. Makes sense.
Yeah. So it's like a, yeah, like a vampire, like the teeth sinking in, and it connects to the copper, which also brings us to wiretapping. That's also where that comes from. They put us like a little bit of a spike in there, it connects to the copper, and then they're able to monitor what's going across those lines. Yes, called a drop. Even to this day, and they don't do it this way anymore, they still call it a drop. And again, this was coax. Well, there was a bit of a problem. If you just cut off the cables and you send a signal down, it would reflect back down the line. So you would get a lot of noise on these lines. So they would actually have to add little boxes on the end of each line to kind of eat the signal, so it would not reflect back down the cable. And these are called terminators because they terminate the signal at the ends of the bus. So, and it reduces noise. Now, as we had talked about briefly, when, like computer A is trying to communicate, and then computer B is also trying to communicate, what happens is as their data is being sent across the line, it will collide and make that data almost unreadable. So if two computers try to transmit at the same time, you have collisions, data collisions. And this is where we were talking about earlier, where they had to come up with a method to work around these collisions so that data could continue to flow. So you didn't get so many errors. So within the computers, they developed something called CSMA, which stands for Carrier Sense Multiple Access. And they added a moniker on it, collision detection. What's happening here is if two people transmit at the exact same time and the data collides, they know that that collision has happened, and then both computers back off instantly. And then internally, they kind of roll a dice, it's like with a million sides, and it generates a random number, and that creates a wait time for them, like how long they will wait until retransmitting. So since both are generating a random number, one of them will get to transmit first. And so that one will start to transmit. If it senses something on the line, it's not going to transmit. And then when they're done, it will transmit. This happens in like milliseconds. So this continues to happen because on a line like this, two computers cannot talk at the same time. So they created this program, Carrier Sense Multiple Access Collision Detection, to kind of work around this problem. And this happens through a couple different topologies. Another problem with the bus is what happens if the hard line's cut?
None of it works.
None of it works. Network goes down. Because not only is it cut, there's no terminators there, so the signal's getting reflected back down the lines. It brings the whole network down. So it has major vulnerabilities. And if this happens anywhere along the line, it can essentially bring down the network. But buses are relatively inexpensive to set up. So that is a bonus of the bus. You do still see them, but they're only in network segments now. You wouldn't set up an entire network like this, but there may be pieces of your network that you do set up like this. We'll talk a little bit more about that in just a few minutes. So that is the ring. Any questions on the ring? Or bus, sorry, bus. That is the bus. All right, next we have the ring, which is you would connect each computer to the next one in the line, creating, in a sense, a ring. Works great in small networks, small offices where you each can share information, fun stuff like that. So I connect my computer to Rachel, Rachel connects hers to DW, DW connects his to Stephanie, Stephanie connects hers to mine. We've created a ring. Problem is now, one computer goes down, you break the ring. So the network goes down. If you cut one line, the network goes down. It's still extremely vulnerable. And we still have to utilize carrier sense multiple access collision detection to make sure that only one person is talking at a time. And we're passing through these communications. Does this make sense? So ring looks like, go ahead.
Like, just to reiterate, like, so if one computer stops working in this setup, like due to like any kind of problem with it, like the whole network goes down?
Yeah, because they're all dependent upon each other.
that seems worse than the last one.
Yeah, I mean, it was faster transmission of data.
Oh, okay. So that's, I guess, the takeaway though.
Mhm. And rings are still used today in token ring scenarios. It's usually in data centers and things like that. They'll use them for network, or excuse me, storage as a network, SANs, SAN. So they still will use token ring in that scenario, but as a open network with all your computers, typically not.
Okay.
Am I off base with that, Greg?
Not aware of the Suns still using that. What it's very possible. I actually don't know about that one.
Okay. It could be my information's 5 years old. All right. So that's the bus, which is a straight line through the ring. Looks like a ring. That's two physical topologies. Nice, right? All right. So now let's erase this one here. And we will create two more computers and a central device. So now we have every computer connecting to a central device. This is called a star. And if you look at it from the top, it looks like a star, right? You have a central device and everything is kind of connecting out from it. So it kind of bursts out in like a little bit of a star pattern. So this is a pretty big improvement because you don't have computers directly connecting to each other. You have a central device that can be utilized to manage communications, like a hub or a switch. And the nice thing is computer A can go down, doesn't affect the network. Computer A and computer B can go down. These three are still able to operate. So individual computers can go down and the network can still function. Unfortunately, though, we still have a single point of failure, which is our network device. If our network device goes down, that switch or that hub, then that does bring down the network. So we've removed one vulnerability in that the individual computers won't bring down the entire network, but we still have a central point of failure. Star networks still to this day are one of the most common network configurations you will see to this day.
And if you were dealing with somebody from the 80s,
The 80s would be the bus, wouldn't it? Your audio broke out, Greg. I can't hear you, man. Still can't hear you. Might have to use your cell phone. We'll come back in 1 second on that. So star configuration, everything comes out from the central device, single point of failure at the central device. But if individual computers go down or individual cables go down, the network can still survive.
Check 1, 2.
Yep, you're good now.
Oh, okay. I was just saying, if you get hired by one of these old school guys, when they first got introduced to this type of topology, they did call it hub and spoke before it got named star.
Okay.
So, you know, you might hear someone say that.
Okay, so open spoke would be another term that you might come across from somebody who's been in networking for a while.
Yeah, 30, 40 years.
Okay, good note. Good to know.
That's what Oscar might call it.
Okay. So you might be asking yourself, gosh, can't we get rid of that single point of failure? Can't we make it so that our network is robust and strong and cannot be brought down? There is a way. It's called the mesh network. What the mesh network does is it connects each computer to every other computer. So it starts out looking like a ring, right? But then you connect to each other. Boom. So every network is connected to every computer is connected to every other computer on the network. So if you bring down this computer, if token ring was in place, you bring this down, then you can no longer continue that communication. But if you bring it down now, A can still communicate with this computer and continue communicating with the other four. It becomes extremely difficult. If one cable is cut, then the computer may not have a direct link, but it can hop to another computer and then where it needs to go. So it creates this giant mesh that is extremely difficult to take down. The internet as a whole is like a giant mesh network because there are multiple connections to each other point. So if a single node comes down, we can work around that. So in essence, the wide internet is a giant mesh network. Now, what could we see would be a problem with designing our networks like this?
Expensive.
Expensive. Why?
It's a lot of connections, a lot of cabling between networks.
A lot of connections, a lot of cabling. That's true. Yeah, that is a lot. What would be another reason, possibly?
This is just a guess on my part, but security issues.
Okay, possibly.
It's a lot of systems to keep track of.
That is a lot of systems to keep track of, but if you have 100 computers, you got to keep track of them anyway, right?
True.
Complexity and troubleshooting. That's an interesting one. Golly?
I would say maybe if you don't, I don't know, if you don't have like a switch or a hub, maybe it'll take like longer to go to the signal to get where it needs to go.
So transmissions would get bogged down a little bit?
Yeah, maybe
Okay.
the speed.
So say we got 5 people here. It's me, Rachel, DW, Golly, Stephanie. We're chugging along just fine. We love the way our network's designed, but we're getting so busy, we now have to hire somebody. And we bring in Rebecca. Now what happens?
It's harder to like fit in a new node into the network.
Perfect. It is extremely difficult to reconfigure the network. That's also true, Oscar. It is extremely difficult to reconfigure the network when you add another node, because then you have to run all those cables to all those computers again, right? Also think about it. Imagine if you had to have hubs, or not hubs, but like network cards on the back of your computer that could attach to 100 different computers. That would be extremely difficult to make. And there actually is a formula to figure out how many cables you would need if you were operating a mesh network. And that is N times N minus 1 divided by 2. N being the number of nodes. You're asking yourself, do I need to know this formula? The answer is yes. So here we have 5 computers, right? So we can plug that in. 5 times 5 minus 1 divided by 2. So 5 minus 1 gives us 4, right? 4 times 5, what's that?
20,
20. Divide by 2.
10.
10. So we need 10 cables if we have a 5 computer network. And you can go through and count them if you want. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 10 cables. Now let's do the same thing with 7. So we have 7 computers. So 7 times 7 minus 1. So 7 times 6 equals what?
42.
42 divided by 2.
21.
21. So we've added 2 computers. And just by adding 2 computers, we've added 11 cables.
I didn't think about it that way. Yeah, that is
So
crazy.
you have exponential growth in the amount of cables you need for every one you add. You can see how quick this can get out of hand, right?
Yeah.
So that is why we need to remember this, that set or the n time, in brackets, n times n minus 1 divided by 2. And how quickly the amount of cables you need adds up for every node you add onto your network.
The way I remembered that formula, I did n squared minus n divided by 2. So that way I wouldn't have to worry about the parentheses. So same concept, you would do like 7 times 7 is 49 minus 7. 21, sorry, it's 42 divided by 2 is 21. So just like another way to simplify the formula for yourself if you want to.
So that is another way we could do it.
Expand it.
So we now know our ring, which is a straight line, I keep doing that. Bus, straight line, ring, circle. Star, looks like a star. Mesh, looks like a spaghetti bowl because you have like all the computers connected to all the computers. And we are now left with hybrid. Our hybrid network essentially is just a combination of any of the other 2. Most common you will see is star bus. Because think about if you have a corporation and they have a big building downtown and they're operating off of multiple floors. So you may have a bus running vertically up the building and a star connected to each one of the bus nodes going up through the building. So you can use the bus to connect multiple stars together. And that is basically what a hybrid is. We have a good little graphic for it on the next page. Do we have any questions so far about physical topologies?
Yes, for the star, you said it used a centralized device. So it's like I'm sorry, I stepped away when you explained that. Is it like a hub or switches that use it with the star or?
Correct.
Like
So with a star, you would have a centralized device, which would be a hub or a switch, and then every computer on that network would be connected to the star, that central device.
Okay, thank you.
So it looks like a star, essentially. Yes, Oscar.
Going back to mesh network, is that, I don't know if we're going to cover it later, but is that similar or the same to the mesh networking that you have with wireless routers today?
To a degree, yes, but it's doing it in a wireless sense. But that's what they're basing this off of.
Okay, gotcha.
Is where you're using multiple nodes and you're using the fastest communication through the nodes.
Gotcha.
Except they would utilize a central command node, which would communicate with the others.
Okay.
Yeah, you have one wired and all of the rest wireless.
Yeah.
Okay. Thank you.
Still a single point of failure. I have one in my house.
Yeah, that's what I'm saying. There's still that command node, which is the primary. But in essence, it still has that communication with each of the other nodes. So good connection. I like that. Rahel.
So my question is, in the bus, if one computer fails down, the network also fail?
With a bus, I'm going to need to confirm this because I believe it's the cable is the point of failure with the bus.
Okay.
If I'm not mistaken, the cable is the point of failure on the bus because each computer is tapping into that cable.
So modern day bus though, I didn't really want to step on your toes on this one. But
No,
a modern
please
day
do.
bus,
I'd rather the correct information be out there.
no, it's you're on point with everything. I just want people to understand how the modern day bus is used. You still have those points of failure because each node along a bus, let's just say, all right, you have a 10th floor building, right? And you have your server room in the basement. You're sending up a Cat 6, and you're going to terminate at like a Cisco, layer 3 switch that's going to do some heavy lifting, right? It's going to start sending to each floor above it to another switch that's going to spread along that floor. So say that you say, okay, this floor 1 is down. That usually it could mean that the switch itself is down, which would mean all other floors beyond that point will be down too, right? So it's still that point of failure that demolishes your whole business. Like all of the other floors above it will be down because the first switch beyond the server room is down, and so forth. So that's point that, yeah.
Go ahead. No, go ahead.
So in the same way as a bus, not necessarily being just a cable, but like the actual device that connects the other device to it, if that goes down, everything else beyond that point goes down.
Okay. In the modern bus, I would agree. I'm speaking more in the classical bus.
Okay.
Where you're tapping into the lines.
Yeah.
So it is a more nuanced answer, but yeah, I agree with you in the modern bus. So,
or I should say the modern hybrid, because that's how they do it.
Bus
sometimes
star.
the bus star, or sometimes you'll have a bus to a switch, and they actually don't come off that switch. They just basically have everyone in that office connect to that same switch on that same floor, and then from that same switch we go to the 3rd floor. If you follow me so far.
Yeah.
So yeah. So inside of that one, in that one device is both a switch and also your bus.
A node on the bus.
Yes, correct.
Yeah. So yeah, that makes sense. To me. Any other questions, please? Yes, Nesanet.
My question is on the star network. So the central device, if it's like down, is it not like supposed to be all day down? Because you say as only like 2 computer only down if it's the central device is down.
No, excellent question. So if in a star network like this is designed right here, if only computer A goes down, it does not affect the rest of the network. The rest of the network works just fine. Only computer A is affected. But say all the computers are up and running and the central device, the hub or the switch goes down, then everything goes down because they're not able to communicate through that central device. Does that clear that up?
Yes, thank you.
Okay, cool. All right, any other questions? I still have 3 people with their hands up. Are you guys just hanging out like this, or do you have questions, Oscar or Gali? All right. So let me erase my terrible drawings here. There we go. Forgot one. So here is much cleaner drawings of what I was just doing. So here we have our mesh network. As you can see, every computer is connected to everything else. You have your bus where you have your central line, and everything is connected to it, also called a common bus. We have our star topology, which have every computer connected to this centralized device, and then they can connect that central device to the internet through a gateway. And then we have that ring network where you can see that just clear definitive ring.
I have a question. The star network is like the Wi-Fi one, right? Or is it actually like physically connected?
Both.
Well, these are physical connections, what you're seeing. So these would be actual like internet cables running from each computer to the central devices or to each other. These would be physical cables run between each computer. Wireless networking typically is considered a star. Unless you add multiple devices, then you can create a mesh, yes. But that is a specific type. This, what you're seeing here, are physical connections. Does that answer your question?
Yes, it does. Thank you.
So any questions on topologies? Do they kind of make sense now?
Could you repeat the formula one more time?
I absolutely can. So we have N times N minus 1. All of that divided by 2. Or if you like DW's version, he has N squared minus N divided by 2.
All right, thank you very much.
Any other questions? All right, since we are now experts on physical topologies, let's talk about types of networks by resource. And networks that contain both clients and servers. Remember, each of us are clients, right? Our computers are connected to the networks. We are in need of resources, so we're connecting to the network to try to gain access to resources. Servers serve up those resources for us. So we are all connected now to Zoom servers so that we can all be in each other's presence. So client server model is what they are basing a lot of this off of. So different types of networks that we can utilize. First one is called peer-to-peer. Basically means everyone is equal. There are no servers. We all connect directly to each other. We all share the networking burden. This only works for small groups. I don't know if anybody remembers having LAN parties when they were younger. You know, we did that quite a few times, playing computer games. And at a certain point, it became difficult to manage. Usually more than 10 doesn't work so good. Not all the networks, Stephanie, use CSMA CD, but we will get into it because there is a device that was created that essentially limits the need for it.
Does peer-to-peer, like, is it limited to just one form of network, like the types that you showed us before?
Well, typically, if you're going to do peer-to-peer, you could do it through a hub or through a mesh network.
Okay.
So you want to keep it less than 10, more than 10, becomes a little awkward. Doesn't work as well. We're all sharing resources with each other. We're sharing that network burden. If I'm connected to a printer, I'm typically sharing it with each other, various stuff like that. So peer-to-peer.
Wait, I'm confused on peer-to-peer. So they share networks, but how do they get like the network?
Well, we're connecting to each other directly, essentially. And we're not utilizing a server or anything like that. We're just sharing each other's resources. Like if I have movies on my computer, you want to watch my movies, you can connect to my computer and watch my movies.
Oh, okay.
If I have files that DW needs, he can go on and grab my files. If I need access to a PowerPoint presentation that Rachel has, I can go onto her computer and get that PowerPoint presentation as long as all that stuff's being shared.
Oh, okay. I understand now.
Yeah. So you're sharing your own networks, right? Your own resources. You're not going on an outside network and getting resources.
Yeah. Typically that is an internal peer-to-peer.
Like
Right.
if, for example, like if we was all in the room together and we're different our own Wi-Fi's and we're just sharing things back and forth like that.
Well, we wouldn't be utilizing Wi-Fi. Typically it would be like ad hoc connections or connecting to a hub or something like that and just communicating with each other.
I don't get it. I'm trying to understand. Like one computer connect, because when I think of network, I'm thinking internet, right?
Yes, but remember our basic definition of a network can be just two computers connected to each other, sharing resources and communication.
Okay.
So it doesn't need to be, because all the internet is just a bunch of computers connected together, sharing resources and communication methods, right?
Right.
But you bring it down to its most basic level, and it's just two computers connected together, sharing information and resources.
Okay.
That is still a network.
Okay, I get it now.
I think if you break it down even further too, if you look at, I think what Daniel just asked about the device is actually important to bring into the picture too. Even though you're not connected to the internet, there are ways to do peer-to-peer. You can actually, in that center right there, it could be a hub right in the center there, in the center of that cross. Or you could have on the back of these devices, network cards, that maybe two network cards, one connected to the neighbor next to you and one connected across the street, for the shortest point of contact to the peer across, just like how it is right there. Say that there's no device there in the middle. They're just connected to each other that way as well. You can do straight cables and crossovers and talk to each other.
Okay, makes sense. Thank you.
All right. No problem.
All right, so peer-to-peer, no servers involved. Everybody's just sharing each other's resources. That's all it is. All right, so now we're going to start talking about different types of networks as well, outside of peer-to-peer. First thing we want to talk about is the PAN, or Personal Area Network. Easiest way to think about this, it's within arm's reach. These are things that you add to networks to enhance your experience. So you would typically have a centralized device, which likely would be your computer. And then you are interconnecting other devices to it to enhance your experience. It could be a direct connection to a printer. It could be Bluetooth headphones. It could be your cell phone, wireless mouse, microphones, You could connect another computer if you're transferring data or utilizing data from multiple things. Basically, it's anything that you're connecting for your personal network. Things to enhance your personal experience. So personal area network within arm's reach. It is extremely flexible. Predominant method for communication is going to be Bluetooth, but other things like FireWire, USB, and others fall into that as well. But the primary wireless technology you're going to use is Bluetooth. Questions on PANs? So personal PAN, small bubble.
I have a quick question.
Yeah, go for it.
Okay, so say that you have some say that you had a question about like NFC and you know, your phone and whatever it is. Would you ever include NFC in this conversation? Would they try to trip you up like that?
NFC would be difficult because it is predominantly used for transactional data changes, and it's very, very
near field.
One, you have to be extremely close, and two, it's very slow. So people would tend to opt for Bluetooth over NFC. You could probably make an argument for it, but again, people are going to opt for Bluetooth where it has higher transmission rates for longer, you know, for more distance than just a few centimeters.
Okay.
You could also make an argument for infrared.
I was just talking about security wise, because Bluetooth is less secure than NFC. So I was just wondering if, you know, there's an argument for that, you know?
Yeah, agreed.
Okay. All right, cool. No problem. I was just curious if, you know, if these guys would ever throw something like that on a test saying, hey,
typically not, because again, you're looking for an exception that disproves the rule.
Oh, no, I'm not disproving. You know, I just want to know if they would say, like, which one of these provide the most security in a personal area network? And they'll throw those in there and then put like probably NFC. And I was just curious if they would ever do something like that.
From a security perspective, you might likely reach a question for that on the cybersecurity analysis or security plus.
Oh, okay.
Not typically on A+.
Gotcha. Thank you.
All right, let's expand that out just a little bit further. And we'll talk about a local area network. Now, a local area network, they would be centralized in a small area, like an office or a building. They're all connected typically by a common medium, which could be UTP, it could be fiber optic, it could be coaxial, what have you. They tend to be connected by a common medium or media, which we know is you know, the types of lines we're using for communication. They allow the sharing of data, peripherals, software, and storage. So we can have file servers attached, printers, all that kind of fun stuff, and they're sharing all of this stuff together in a local area network. Provides very high speed at low cost. And the topologies that you would typically see on this include your bus, star, and ring. Printers are always a menace, Kevin, but you will learn that next week, I promise.
I've known it my whole life. Like my mom used to have like an all-in-one printer that like faxed. It did everything, and it was every day. It was something with it.
Oh yeah. They break down. They're all kinds of fun.
It got worse when the printer got. Then we got a Bluetooth printer, and it got even worse.
And then you have WPS, which is like the biggest security risk ever. Everybody loves it. We'll learn about that. All right. So let's reconfigure the LAN just a little bit, and we'll talk about what most of us use in our houses, which is the wireless LAN, which is the local area network but we've removed the cables and we're connecting to everybody wireless. So we're not having to run physical connections to the communication medium. It's all going over the airway. These can be very public and extremely unsecure, or private and kind of secure. And thankfully, the best part about these is they're still relatively inexpensive, but they provide a lot of flexibility and mobility. So you're not tethered to a wall or to a particular spot. You can move around as you need to. Any questions on the WLAN, or wireless local area network? So we go back. PAN, personal, arm's reach. LAN can get up to the size of a building. It's a single network, about the size of a building.
This one would get me. The question would get me because at the last line there, it says LAN topology includes a bus, star, and a ring.
Yes,
Yeah,
would fall
yeah.
under the LAN.
Yeah. Oh, okay. Okay. Even old school. All right. Never mind. I thought
Yeah.
you meant like what's popular today. I was like, what? What? They still
Yeah.
have ring and bus in your house? Okay. Gotcha.
I'm sure there's an enthusiast out there somewhere who does.
Okay.
And I guarantee you there still are offices where they do not have high-speed internet, like in certain areas of the country where they don't have high-speed internet, where they still run an old school bus, like a coaxial bus.
Wow. Mm.
Not to say it's
Seen it in
you'll
the
do that.
ceilings.
Yeah.
Yeah. But
You'll still see the wires running the ceilings, even in buildings today, but it's not common that you'll come across it, but it is possible. Yes, Kali.
So you say the PAN is like inside your house, like, or like a hotspot or something? Or I'm sorry, I'm confused on
So
that.
when you're walking around with your phone and you have Bluetooth headphones in, you've created a PAN.
Okay.
You have two devices connected together.
Mm-hmm.
The phone becomes your centralized device. So you can have your headphones attached to it. You can attach it to a game controller if you wish, or whatever. So the phone becomes a centralized device, and you've created a personal network just for yourself. And you've added other devices like headphones or whatever to enhance that experience, creating a personal network for you.
You might want to go back to the slide for Gali.
Yeah, but I say, what kind of topology is that one? Like, is that like does it have a topology, or is just like it just by itself?
The best you could associate it with would be a star.
Oh, okay.
Because you would have that centralized device, which would be your computer, or if you're out and about, maybe your phone. But say at your house, maybe you have your phone connected to your computer, you have your wireless headphones connected to your computer, or wireless keyboard, mouse. All of these devices create that network.
Okay.
Because you're utilizing wireless technology to communicate with your keyboard and your mouse and all that fun stuff.
Okay. I was getting that one confused with the LAN because I keep thinking house, like you in your house. So, and then okay. Okay.
Well, that would be, see, a WLAN, if you got 5 people in your house, they can all be running off of this WLAN. And you're all talking to each other. So it's no longer personal, right? It's not just your stuff. You're communicating with everybody else.
I thought the LAN was like more like multiple LAN connected, like over like a wide area, like
well, a LAN
like
could be 10 people in an office. It could be 10 people in an office, or 5 people in an office, or 1,000 people in one building.
Oh, okay.
He's touching on it though. You're getting there, right?
Yeah, he's getting there.
Yeah.
We're getting there. Yeah, you're getting a little bit ahead of us to other networks.
No, yeah, because that's the way I read it in the book. That's why I'm thinking of just like, I'm not thinking, they didn't describe it as like people. It just described it as like areas. So I'm just thinking,
and that's
like,
what it is it's more geographic locations. So personal, arm's reach. It's right around you. LAN goes out a little bit further, can be the size of a whole building. It's still one geographic location, but it's like a whole building, right?
Mm-hmm.
Or a whole house.
Okay.
But it could be as small as one apartment in an apartment building. or one office in a skyscraper. That could be a single LAN, or the whole skyscraper can be a LAN. But it's still one geographic location.
So it just mattered to what people are connected to, like that network, like that they're all connected to. All right. Okay.
So the WLAN is just, go ahead.
No, I was just saying something you can't get from the book. When you read it, it's just not registering the right way. I guess.
Well, that's why we come together and have that that discussion, right?
Which is awesome.
So WLAN, just like a LAN, but you're not using physical cables. You're using wireless. Same thing, but it's WLAN, not to be confused with a WAN, which is right here. So WAN is something different. We'll get to that. So WLAN is just like a LAN, except it's wireless and it's off of a single node. So it's a single node or a single network device right here. Because we actually have wireless mesh network, or WMN, which is what Oscar brought up earlier, where you have multiple wireless devices scattered across, connecting together a network. You will have, in general, a controlling router, main router, and then you have other routers that will support it. They will all operate as if they are a singular piece. So the SSID, or the name of the network, and the password of the network remains the same for all the devices. And it just kind of hands you off as you get closer to one or the other, or if traffic is heavier on one than the other. So they kind of juggle you around based on your position in the network. But it allows a wireless network to extend beyond what would be possible for just a particular WLAN with a singular device. You see these a lot in big office buildings, hospitals, universities, things like that. They will use a wireless mesh network to kind of spread that signal out across the area so that more people can connect to it and you have greater connectivity across a larger area. But it is primarily controlled through your main one. If you change the password on your main device, it's going to push that password out to all the others so that everybody else stays on the same page. And these devices where you communicate with the network, so right here, that main device is called a WAP, a W-A-P, WAP, or wireless access point. Any place where you go to actually connect to the network is called an access point, or AP. These individual are called WAPs, wireless access point. Here you have multiple WAPs, or ways to access the wireless network. Questions so far? So wireless mesh network. Go ahead.
No, saying they're getting really reliable too. Ubiquiti has a super redundant line I want to get into. Basically, they have where you do a mesh with, so that you can have multiple devices with multiple hard wires, and they all talk to each other, and any one of them go down, the other one picks up right where that left off from a hard line perspective, and they still are connected to each other wirelessly. It's pretty cool. Yes. Plus you have a, like I have the Pro here, the UFI blah 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 Pro, and on that same device you have a physical secondary connection that you can tether to the next one physically, and you can have like 5 points of entry, like physical points of entry, and then those are connected to another physical device, and then they're mesh wirelessly. It's really cool. Like, it's so redundant. If you should draw lines, it would be, you would just cover the sky. There's so many. Yeah,
that is very true. But yes, they have come a long way, especially recently. Early mesh networks were a nightmare. especially the ones in the personal market, like that you would use for your home or something like that. Comcast put out one. I tried getting it functional in my cousin's house, and we could not get it to work very well at all. More recent renditions work beautifully, but just the early technology just wasn't quite there. But yeah, they've come a long way in just the last few years. All right, so we've talked about our PANs, our LANs, our WLANs, and our WMNs. So wireless mesh networks. Now, what about a MAN? Which is a metropolitan area network.
Sometimes I think you're making these up, Kelly.
I am. You just won't know until the test, will you? So you have a metropolitan area network, which is, it could be just a couple buildings up to a city. So a metro area, metropolitan area network. So if you have, like here in Jacksonville, we have Florida State College of Jacksonville, FSCJ, and they have multiple campuses across the city. So they actually have a MAN network established. So all these buildings are still communicating with each other on the same network.
Is the next one gonna be a woman?
Oh, well, yeah.
A wireless.
A wireless man.
A wireless, yeah, wireless man.
Wireless, yeah, woman. Wireless on the
metro area.
online metro area. There we go. Yeah, we could probably make that happen. No, so it covers a few city blocks. They actually have something called a CAN, which is a campus area network. But they don't dive into that until Network Plus. But there is something out there which is just strictly for like a university campus or something like that. But if you see campus or a few city blocks or something like that, with regards to A+, it is a MAN, a metropolitan area network. So size of a city. Got to go out a little bit further now to a WAN, which is a wide area network. So much larger geographic scale. This could be an entire continent. This could be multiple continents connected together, what have you. Essentially up to a global network. And that all includes a WAN, wide area. So when you're thinking about these in geographical terms, I think last cohort we were joking about if they were going to create a PAN, another type of PAN, which would be a planetary area network as we start developing, with Mars and the moon and all that stuff. What they're going to call that. Curious to see. Oh, what?
IPAN, interplanetary.
There you go. Or it's called a PLAN, a planet area network. So are we clear on the physical network types, like geographical, how much space they take up, starting with the PAN, which is the smallest, all the way out to the WAN, which is the largest? Yeah? Very good.
Yes, sir.
All right, it's 10:40. So let's take this question from Rebecca, and then we will pause and take about a 5-minute break for sanity. Yes, Rebecca.
So what's the advantage of using the wire mesh networks, the WLAN?
No, wireless mesh network is WMN, yes, right here.
WMN, sorry.
No problem.
I really didn't get, so if one of the routers or the disconnect, so is it they can use the different one? Is that what the advantage of it?
Well, here's the thing. So say I am my annotator. So say I am here and I am kind of walking through the building, right? At a certain point, I'm going to be out of reach and not able to communicate with this router, right? Or WAP. So what it'll do is it'll hand me off to this one here because I'm closer. So I'll start talking to this one. But as I walk through, I may get out of reach of this one and I can't communicate with it. So then it will hand me off to this one because I'm closer. But I will not notice any of this. This will happen seamlessly. My device will jump from one to the other, depending on which one has the strongest signal, and allows me to continue communicating with the overall network.
Oh, okay.
Does that make sense?
Yes, now I got it. So if one of them disconnected, is it gonna have a problem with the other ones, or nothing's gonna happen? They can
say this one
connect.
disconnects, right? So this one over here disconnects. So now I can communicate from my main router. I can jump to this router and then jump to this router and then jump to this router. So I can still communicate through the network even if one goes down.
No, it doesn't affect any of them.
Well, if somebody is over in this area, they would hand me off to one of these other two. I would have a weaker signal, but I would still be connected.
No. Okay, got it. Thank you.
Not to complicate things, but before this, they used to have repeaters. Well, they still have repeaters now, but in repeaters, basically, you are re-authenticating, even though you're using the same username and password, but you're pretty much re-authenticating to the next device. Instead of seamlessly handing you off, your device disconnects from the router 1 and connects to router 2, or WAP1.
Which, if you're on a phone
WAP2.
call, it drops the call.
Yeah, so you have to re-authenticate to get reestablished connection. So this is a really cool way of, just seamless walking through an airport, hospital, building, house.
You don't have to re-authenticate every time because it's the same thing.
Yeah, you should see me in my attic.
All right, Bernard, did you have a question?
Yeah, I was gonna say, I think y'all kind of said it, but as a small understanding, I could look at that as like cell phone towers as well. Like as I'm going from place to place, it's connecting to the next tower or router. If I'm looking at it as that term, in a way I'm trying to understand it.
That's a beautiful way of looking at it.
Okay, all right. Yes, sir.
I like that analogy. It's kind of the same. So thank you, Bernard. I like that. Yes, Scotty, did you have another question?
Yeah. So okay, now I see what Oscar was saying before, because I didn't really understand what he meant beforehand. But so the first mesh that we saw in the physical topology, that was like over wiring, that was like with wiring, and then this one is like wirelessly.
Yes, all of these are physically connected by wires.
Oh, okay.
So when we get to wireless mesh here, they're communicating wirelessly. There's no wires between them. There can be, but in the sense that they're saying here, there is no wires between them.
Oh, okay. Okay. So I guess like in the test, if they ask you a question, or I don't know how they would ask you that, but they would specify if they're talking about the one with the wire and the one that's wirelessly.
If they do not say wireless, assume wired.
Okay.
But if they're using wireless terminology, like they're saying Bluetooth or something like that, then you need to understand that they're speaking wireless. So if they are not specifically pushing you towards wireless, you assume wired.
Okay, yeah, because in my head, I'm thinking mesh and I'm already thinking like wireless. I don't know, it's because in the age we are now, but like I just think meshing is just wireless.
It's because of where we are at this point where most things are wireless. However, you still get your highest speeds and robust connections still through wired connections.
Okay. Okay. Thank you.
Any other questions?
Question.
Yes.
Mr. Kell. So the difference between the mesh network and then the metro provide. So is it how the area, the size of the area is, like how large? Does that the difference between?
Are you talking about the difference between which one, like this one and
the man? Yeah.
And the
metro.
WLAN?
No, the next one.
Okay,
so
the wireless mesh between that and the MAN.
Yes.
So wireless mesh would still be pretty much over, like a small area, like a building or something like that. Where metro, although It's one of those, like, we're going to get into some technicalities here. Some mesh networks can be the size of a campus or something like that. They do have them on our campuses here, but this would be a wired connection the size of a city. This would be a wireless connection the size of, probably a large building or multiple buildings.
College or university or something. Okay.
The key in this would be the wireless utilizing multiple devices. So mesh, wireless mesh.
I'm sorry, for the metropolitan, you said wired or wireless?
This is typically wired.
Over a city? You said over a city?
Yeah.
Oh, okay.
Yeah, over a city. Cover a few miles to tens of miles. Make sense?
Yeah, a little bit, yeah.
Okay.
I'm getting there.
All right. So you go ahead and pause the recording right here. So start a recording again. See here, Danielle, can you please read for us real quick on the network interface card, or NIC?
Network interface card. Provide the physical connections between the computer expansion bus and the network cables. Boost the digital signal from the computer. Change the data stream from wide stream to narrow stream, parallel to serial conversion. Move data to and from random access memory RAM, and manage the flow of data to and from the network cable. Buffer the data from the computer.
There we go. A really, really elaborate way of saying it allows your computer to communicate outside of its box to the network, to other computers, things like that. So it's controlling that flow of information. Sometimes your computer moves faster than your network, so it buffers it. Sometimes your network is sending information faster than your computer can absorb it, so buffers it on the way in. But this is the primary device that allows us to communicate with our networks. All right. Uh-oh, we got to get into the ones and zeros a little bit. So, binary, who remembers their binary lesson from Coursera? All right, Tomas, take it away. No.
This one.
So, okay, so from our lessons, let me pull up another one here. Let me grab it real quick. Just do a quick. Where did I put it? Ah, here we go. Let's throw this up over here. Hold down that thing. So in Coursera, they kind of gave us a little bit of a lesson where they said all the binary is kind of letting you account by using the on-off mechanism of the binary code. And so when we have 8 bits put together, we can count from 0 to 255. If we remember that from Coursera, right? Then they gave us that little bit breakdown sheet where we kind of go through and we add it up. So like, let's go through this here. Shamika, can you give me a number between 1 and 255, please? Or 0 and 255?
72.
72. All right, so let's go over here. So let's go over to the here and we'll say 72, right? And this is our calculator essentially. So how you get this is you start at 1 and you double each time for 8 times. So you got 1, double it, you get 2. 2, double it, get 4. 4, double it, get 8. 8, double it, get 16. 16, double it, get 32. So each time it's doubling, the 8th bit will get you up to 128. This was how I was taught how to figure it out in binary. I would start out by just writing this little graph down. 128, 64, 32, 16, 8, and then just draw a little chart. So this was one of the things I wrote down for my network plus because we needed to know binary network plus. You don't necessarily need to know it for A plus, but this is kind of letting you know where these numbers come from. So we have the number 72. So I look at 128. Can I subtract 128 from 72 and get a positive number? No, right? So I leave that at 0. I move on to my next number. Can I subtract 64 from 72 and still have a positive number? I can. So I make that a 1. Come over here, subtract 64. What am I left with?
8.
8. So now I have 8 left. So I go to 32. Can I subtract 32 from 8? No, stays a 0. Can I subtract 16 from 8? No. All right, stays a 0. Can I subtract 8 from 8? Yes, I can. Gives me a 1. 8 minus 8 equals what?
0.
0. There we go. So I can't subtract 4 from 0 to have a positive number. Stays 0. Can't subtract 2. Positive number. Can't subtract 1. Positive number. Boom. Our binary representation for 72 is 0, 1, 0, 0, 1, 0, 0, 0. We have now counted to 72. Want to try this one more time?
Yes, is the numbers always going to be 1, 2, 4, 8, 16, 32, 64, and 128?
Yes.
Okay, even if you can go to 255, can we do one that's more than 128?
We absolutely can. What number would you like to do?
255.
Well, let's go a little bit lower than 255.
175.
175. Perfect. So we will start with 175. We're going to get our binary representation of 175. So let me go here. Let me zero us out again real quick. And also, if you watch this upper number up here, it will show you as we're adding it up. So this upper green bar right here, I'm going to give you guys access to this spreadsheet. So 175, can we subtract 128 from 175?
Yes.
Yes. All right, so what do we do?
So subtract 128 from 175.
So we put a 1 there, correct?
Yeah.
And then we subtract 128 from 175. What does that leave us?
47.
47. All right. Can I subtract 64 from 47?
No, so that's a 0.
So this stays a 0. Can I subtract 32 from 47?
Yes.
All right, so what do I do?
So it's a 1 at
1.
32.
So we do 32 here. So what is 47 minus 32?
15.
15. All right, can I subtract 16 from 15?
Yes.
No.
No, so what do we do?
That's a 0.
0. Can I subtract 8 from 15?
Yes.
All right, what do I do?
That's a 1.
A 1. So we had, 16. And then we subtract 8.
No.
Excuse me, that was 15. My apologies.
15. Yeah, we can subtract 16, take away 15, no?
No.
Well, we can't do
You can't take
15, take away
from-
16.
Oh, yeah. Okay.
That's what we were doing. So now we have 8 left, right?
We have 7 left.
Or 7, excuse me, 7. I'll get there. So 15 minus 8 equals 7. So can we subtract 4 from 7?
Yes.
All right, what do we do?
1.
Make it a 1. And as you can see up here, we're now up to 172, aren't we?
Mm-hmm.
So we make it a 1. So now what do? We subtract 4 from
3
7, right?
Yes.
Gives us 3, correct?
Yes.
Or 3. Now, can we subtract 2 from 3?
Yes.
What do?
We put a 1.
Put a 1. And what do we do when we subtract 2 from 3? What's left?
We have 1.
1 left, all right? Can we subtract 1 from 1?
Yes.
What do?
We put a 1.
Put a 1 there, right? So now we have, and we can see 175, 175. It matches, right?
Yes.
So now our binary representation for 175 is 1 0 1 0 1 1 1 1. That is how we represent 175 in a binary bit. Is this making sense to us now?
Yes, thank you.
Yeah. Yes.
Anybody want to do one more run through it, or are we okay for right now?
If you don't mind, can you do one more?
I can
stepped
do
out
one
for a
more.
second.
I just need someone to give me a number.
So, Mr. Kelly, what is the last number? Oh, sorry.
What do you mean? What is the last number?
Oh, the 4th row. It was 118, whatever. It's already deleted out. So the 128, 64, 32, 000, is that the numbers minus?
Well, what this is
The 4th row.
What
If you
it
go
is
to
like
200.
the 128 is what that number would represent in binary.
Yeah, but the last one with the brown.
Right here.
Yeah, if
Or
we
in the
go
bottom?
to 220, yes, that's the one, 224. So if we go, the 224 gives us 128, 64, 32, and 000.
Yes.
So what's that number? Is that the number we subtract from the top one to the bottom?
Oh,
With this number down here, or you talking about up here?
Yeah.
Well,
She's talking
basically,
about the
what
last
it's saying,
row.
what it's doing is that's the formula. So what it's doing is whenever there's a 1, it carries the number down. Whenever there's a 0, it does not carry the number down.
Okay, so that's
So it's
the
basically
subtraction numbers.
It's saying that like all of this is adding up, this bottom row, to equal the green number up here.
Yeah, okay.
It's like a use, not use. Like I'm using that number, I'm not using that number. If it's a
Yes.
0.
Correct.
I think a good one to do is actually the 255, just to show everyone that if you add from 1, if you add all those numbers up, it equals 255.
Okay.
So 255 would be all ones across.
Yes. So you can see, like, remember up here is the everything added. So what he's saying is if I do 1 plus 1, 1, you can see it going up each time, right? If I turn all the bits, all 8 bits on, I get 255. If I turn them all off, I get 0. Now here's another one that kind of works. So for 128, if I want to get 128, what do? I got to do 1 0 0 0 0 0 0 0. So I'm only turning on the 1 bit, and I get 128, right? We understand that? So 128 just equals 1 0 0 0 0 0 0 0. Because I've only turned on the 128 bit. Is that clear? Now,
yes.
So here's an interesting thing. If I turn on every bit before it, I'm going to get 127. So I will be 1 less than that next bit. And that happens all the way. So if I wanted to get 63, so I take 64 minus 1, and it would be every bit before the 63 would add up 63. And then in order for me to get to 64, I'd have to turn all of these off and then turn this one on. So for each one of these, you have to add up everything before it. Does that make sense? Or am I making this worse?
Let's run a lower one, Kelly, if you can. Let's run 65, and then we'll go over it again so that maybe we can go over step by step.
Okay.
This definitely explains it better than the video.
All right. So give me one more number, and so that we can walk through creating the binary again. So like if I have 4 and I want to get 4, I turn on 1 bit here. That gives me 4, right? So you can just look at it as 1, 0, 0. That is my 4. And what's happening is each time you turn on a bit, you're counting up. So I have 0, they're all zeros. To get 1, I have 1 bit. So it's all zeros and a 1. That gives me 1. If I'm going to go up to 2, I turn on the 2-bit, and the 1 bit becomes 0. So now I have 2 because here's my 2 position. If I want to get 3, I turn the 1 back on. Now I have 3. And I'm 1 less than 4. So if I want to get 4, I turn the 4-bit on. The last 2 are off. So now I have 4. I've gone up 1 higher. To go 5, I turn on my 1 bit, and it just keeps going up like this. It's ticking up slowly each time. But we can go through and do another number if you want. DW, do you have an idea of one?
Yeah.
Just
let's do like 140.
140.
Yeah. Let me can I try explaining it while I use
yes, please. Please.
All right. So Ebony, so remember that we use binary for up to 255 representations, right? Because 0 is 1. So you have 256 places, but you can only represent up to the number 255 because 0 takes up one of those places. Okay, so now each one of those places represents something, right? So the letter A or the letter 1, right? But so by using these places, like let's say the number 140, does anyone have a chart handy? Do you have the chart, Kelly?
For 140?
The ASCII chart. Let me see if I got one real quick.
Yeah, I don't have that handy.
Okay, all right. Well, that goes beyond that. All right. So let's say we want to represent the value 140 in binary. The way that we would do it is we would take 140 and this chart that Kelly has up, we start with the last bit, which is the 7th bit, right? And the 7th bit represents the 128. So you take 140 and you subtract 128 from it. If you can do that, okay. So this is the ASCII table. This represents what each binary number from 0 to 255, what character it represents. And this is pretty much how the language is, how we represent language to computers. What's that, Kelly?
Yeah, I was like this, but this only goes up to 127, I believe.
Okay.
Because you can represent 0 through 9, and this is how we get our alphabet in code. But back to here.
Right. So you would start off for 140, you would take 140, and then you would subtract 128, which is you start with bit 7, right? And that's on, right? So 140 minus 128 should give you 12, right? All right, so the next bit, which is bit number 6, is 64. Can you subtract 64 from 12, Ebony? No. So then that stays off, which is a 0. 0 means off, 1 means on. All right. Now the next bit is 6, right? Which represents 32. Can you subtract 32 from 12, Ebony? No. So that bit stays off as well. The next bit would be 16. Can we take 16 away from 12? No. So then that stays off as well. Okay. So the next bit is 8. Now we can take away 8 from 12, right? We can, and we will get a remainder of 4. So that bit goes on. All right. Now, can we subtract 4 from 4? And we can. So the bit stays on for that, or it goes on for that one, right? And then you get 0. So the rest, for, you know, you can't take away 2 from 0, so that stays off. And then you can't take away 1 from 0, so that stays off. All right. Now you look at those numbers that you have and you read them 1 0 0 0 1 1 0 0, and that is your binary representation for the value 140.
Does that make sense? Correct. If you can't subtract it, it stays off. Exactly. Now, again, I'm going to make this Excel sheet accessible to you guys. Make a copy for yourself. Use it for practice, because this is how we're going to be creating. This is how you create IP addresses. These 8-bit binary representations. That's where it's coming from. Okay. All right. So we're
Thank you,
okay.
Kelly. This was better than the videos that I was watching on YouTube. It was you broke it down really easier. So if the number can be subtracted, it's a 1, and if it can't be subtracted, it's a 0.
Correct. Which is why I always say it's really good just to draw out this chart. And you just start, you know, if it's easier, you start from this side and you just go 1, 2, 4, 8, 16, 32, 64, 128. And you just double it each time until you get 8 columns. Start it out, then you start with your number and you just move left to right, making these subtractions, and then you can create your binary that way. And again, it's exposure, it's practice. Will you have to, you know, convert binary numbers for the A+? No. Does it help to have an understanding how these are created, to understand a lot of the concepts that we're going to be talking about? Yes.
Yeah, but even in the A+, you might not know it for that, but when you get into work, you might have to convert binaries. So you definitely something that you should have in your tool belt as a IT, you know, professional.
All right. Now, not to be mean, but you may be asking yourself, we have a bit, we have a byte, and then it goes up into megabytes and kilobytes and gigabytes and all that fun stuff. Why on earth do we have a nibble? Does anybody remember what a nibble is?
4 bits.
4 bits. So we
Or
could
half a
do,
byte.
what is it? 1, 2, 4, 8, right? So half of a byte, 4 bits. Well, in order to make things a little more efficient, binary is kind of inefficient, or using the straight, you know, binary to numbers rather inefficient. So they actually started using something a little more efficient called hexadecimals. If any of you ever saw the movie The Martian, when he's trying to figure out how to communicate back and forth with NASA really quick, he's like, hexadecimals, hexadecimals to the rescue. This is how we're going to make it easier. This is what he was talking about. Instead of having 8 bits and going 0 to 255, we now have 4 bits, which give us 16 places, or 0 to 15. Well, we can't just put in 15, because how would we tell the difference between 15 and 1, 5? correct? So we start using letters. So they use 4-bit representations instead of 8, makes it a little bit easier. So 4 zeros equal to 0. You turn on your first bit, you get a 1. And then it's just like we were doing, where you kind of add everything up until you get to 9. And you can see the bits adding up over here. It's the exact same thing we were doing. Instead of going all the way to 128, though, you just go 1, 2, 4, 8. There's only 4 places to know. Once we hit 9, we've done 0 through 9. We can't do any more single numbers, right? So when we hit 10, we call that A. When we hit 11, we call it B. And we're just converting it to a letter. So instead of just using straight numbers, we have numbers with a mixture of letters, and that is called hexadecimals. So let's try it out. Let me get my annotator out here. So we will write out our little chart. So we have it. We have our 8, 4, 2, and 1. Just draw it out here. So somebody give me a number between 0 and 15.
3.
3. So we'll say 3. Over here. Can we subtract 8 from 3?
No.
No. 0. Can we subtract 4 from 3?
No.
No. So what do we do?
0.
0. Can we subtract 2 from 3?
Yes.
All right, what do we do?
1.
1. Can we subtract 1 from 1?
1. Yes.
What do we do?
1.
1. Now, give me another number, like give me something higher than 10.
12.
12. Okay, so we have 12. Can we subtract 8 from 12?
Yes.
All right. So what do we do? 1, right? What do we have left?
4.
4. Can we subtract 4 from 4?
Yes.
All right. What do we have left?
0, 0.
0, 0, because we have nothing left, right? So here's our binary representation, but we looked at in our chart, 12, we can't say 12 because we won't know if it's a 12 or if it's a 1, 2, right? So we'll go down to our chart and we'll look. When we hit 10, it's A, 11 is B, 12 is C. So 12 equals C. That's all they're doing.
On the test, would it have this chart? Or we have to know it?
No, we would have to recreate this. But we know what we can remember, what we need to remember. They're not going to make you convert to hexadecimals either. But this leads to how you will know if a number is invalid. Hexadecimals go from 0 to F. F is in Frank. Anything over F is an invalid hexadecimal number. So if I put H or G or L, any of those cannot be represented in hexadecimal. So it can either be a 0 through F. Does that make sense? Because F is the highest number we can do. That's 15. Based on our chart here. So make a little bit of sense? Getting some yeses, can I get some head nods, thumbs up, still shaky?
So the number 312, we just pick a random number. There is no any number we just pick any number.
Well, no, I was using that to kind of show you how to get the binary from the number. So, but I like where your head's at. Let's up the difficulty a little bit and remove the chart. So if I say, what is my binary representation for let's say E. So we want to figure out what E is. We see that on our hexadecimal chart. So how can we figure out how to get to E?
Wouldn't that just be 14 or no?
Yes, it would, right? E, because if we actually go, we can go back and we can mentally write it down, you know, our 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I write terrible. A, because we can't do 10. B, C, D, E, and F. So that gets us 0 to 15. So we're going to find 14, right? Which was E, which Gali called. So how would we get to 14? So we have 14.
Subtract 8 from 14.
Okay. So
And then
8.
8 is a 1.
So 8 is a 1.
We have 6 left.
Okay.
We can subtract 4 from 6, which is a 1.
Okay.
We have 2 left. So we can subtract 2 from 2, which is a 1. And we have left. So, and we can subtract 1 from 0. So that's a 0.
Beautiful, Mildana. So we now have created our hexadecimal. We see the hexadecimal E. We know that equals 14 in our brains because we can count up from our little chart here. 1 to 14. So we hit 9, then it would be 10, 11, 12, 13, 14. E equals 14. And then we just come back to our nibble. 8, 4, 2, and then we don't need the 0. Gives us 1. And if all the ones were on, what would that equal?
15?
15 or
F. Or F.
F. F. Because we can't put in 15 because we wouldn't know the difference between 15 or 1, 5, right? So we use F to represent that. So yes, Oscar, perfectly. 15 equals F, which also equals 1, 1, 1, 1, binary. Very well done. Yes, Kevin.
Just what is the? Can you reiterate like what the actual purpose of a nibble is? Like because you know we have bits and we have bytes, and that's all I've ever heard of. Like why are
how many bits are in a byte?
8. Oh, 8. Then there's 2 nibbles in a
2 nibbles in a bit, right? Or in a byte.
Yeah.
So we can use a chunk of 4, which is a nibble, to create a single hexadecimal character.
Oh, and that makes more possible. Okay, alrighty.
Makes more possible options.
Yep, I can see that. Okay, alrighty. Thank you for clearing that up.
No problem. I like the question. Yes, Gali.
I get what you're saying. Okay. I get what you're saying, but like I just wanted to understand. Like I understand the concept, but when you say you can't tell the difference between the number 15 and like I don't understand what you mean by that. Like, well, what does that mean?
Okay, so binary wise, you wouldn't be able to tell the difference between or gosh, give me 15 in binary, which would be so 1, which would be 0, 0, 0, or excuse me, I'll just do it in nibbles to keep it even. So 1, which would be 0, 0, 0, 1, and 0, 1, 0, 1. So you wouldn't be able to tell the difference between all, excuse me. Undo.
No, do it in bytes. You have to do it in bytes.
Yeah, there we go. So here you go. So you wouldn't be able to tell the difference between this and these two together. So here's the binary for 15. Here's the binary for 1 and then 5.
I mean, what do you mean? I mean, I'm sorry, but like they're clearly different. Like the ones and the zeros are different positions. So what do you mean you wouldn't know the difference?
You wouldn't know the difference if that was being put in binarily and it's being translated for you. If you're looking at a 1, or if you're looking at 15 as a number by itself, or 1 and 5, which can make drastic differences in how the code's going to operate.
Okay.
Does that make sense?
Not really. Maybe I'll understand more down the line. I got to read more on this. Like I understand the concept, but it's just, I don't know. There's something I'm missing that's not clicking in my head right now. So.
Okay.
I think I think I understand what he's saying. Like the reason why you would need to differentiate between that, I think, is why you probably need to talk about it, because I can simply, in binary, if I wanted to find 15, all I do is put like a bunch of zeros and like from 8 onwards, or 8 down, I should say, like 8, 4, 2, and 1 equal 15, because that's right before 16, right? So I could represent 15 in binary, but why would you need to do it in nibbles is what he's asking.
Well, this is where we're going to talk about, when we get into like IP version 6 versus IP version 4, how we write it out. And then it allows us to compress a lot more code into a shorter space.
Yeah, that's a good
Thanks,
thing.
Greg.
Yeah,
I think that's exactly what I was like. That's why I'm like, maybe down the line I'll understand it more.
Yeah.
But I still get the concept, so I still know what's going on. But I just,
I mean, when we start talking about like compressing the code down so that you're using fewer spaces to represent bigger chunks of binary, that's where we're going to be going.
Gotcha.
Make sense?
Yes, sir.
Like shortwave transmission.
Yeah, one way to look at it. Kevin, did you have another question, or are you good?
No, I'm good, Kelly.
All right. Modanat, did you have a question, ma'am?
Yes. The hexadecimal.
Yes.
The writings, because you know how they write the E0 with the column.
Yes. Like this right here?
Yes. So how do you represent this? The E0 and
so the E, so I'm sorry, go ahead.
Yeah, you started already.
So this would be an E and then a 0. So like these two pieces of information right here together represent 1 byte. So you would have E, which is 15.
14.
Here we go. So E, which is 15. So it's 1, 2, 3, 4. And then you have 0, which is 1, 2, 3, 4. So we've now represented it here. Where in binary, if we wanted to do the same thing, go over here. If I want to do the same thing, I have 1, 1, 1, 1, 0, 0, 0, 0, 0, which gives me 240. So I could either represent it as 240 or E0, correct?
Can you please come again? And I didn't see your writing.
Sorry. So come back over here. Wrong screen. Boom. So we have E0.
Yes.
So each one represents 4 bits or a nibble, right? So E0. We could put those together and that would be 1 full byte, right?
Mm-hmm.
So E and then 0 would be E, which is 15 right here. It's 1, 1, 1, 1. So I put that down here. 1, 1, 1, 1.
No, E is 14, right?
No, E is 15. Oh, sorry. You're right. I apologize. I have made a mistake. I absolutely apologize. So thank you for that. Let me get that up here. So E would be 1110. Thank you for that. And then 0 would be 4 zeros. 1, 2, 3, 4. Does that make sense?
Yes.
All right. Now, if I went over to my ANDing and I put that in here, I put it in incorrectly. So we have a 0. So I would be 224. So I'd have 128 on, 64 on, 32 on, and then the rest of them off. That would be the exact same thing as if I typed this right here, right?
Yes.
So, but instead of using 3 characters to identify that, I'm now able to do it in 2. I've saved space.
Okay. So CB will be 1100 and 1011.
Correct. So you have C, which is 1100, which is the first part of it, and then B, which is 1011.
Okay, and then you go back to the
Well, no, what I'm saying is if we were doing it the old way, it would take up more space.
Yeah.
What this is doing is allowing us to condense more information into a smaller space. That's why we use hexadecimal. Does it make sense?
Yes, I understand now. Thank you.
Okay, no problem, no problem. Bernard.
So just a small understanding, the way you're saying it is the reason why we use it is basically doing from addition to multiplication. So we still got the same information, but we just I wouldn't say simplifying it, but condensing it down so that we can get all the information from 10 to higher numbers from 0 to 9.
Or 0 to 15.
Well, 0 to 15.
Yeah.
But I'm saying like, okay, if we writing it 0 to 9, that's the first regular, well, you said 0 to 7 is 8 bits. And
yeah,
then,
well, no, 0 to 9 would get us like the first 10 placements. And then we have 5 placements left over, and that's why we go A to F.
And then from there you go A to F because you don't know the difference between like you said, the 0, 1, 1, that could be 1 plus 1, which gives you 1, but also we got to add the A's and B's because now it's like multiplying because we want to condense the 1 and 5 because we don't know the difference between the way it's.
Well, I mean, not exactly multiplication, more like, I mean, and I understand it in a basic sense, multiplication is repeated addition, but this would be, you know, adding 4 bits plus 4 bits plus 4 bits, and we're just taking it in smaller chunks and just making it easier to translate.
Yeah, that's basically what I'm saying. Just trying to, in my mind, condense it down to dumb it down to a smarter, I mean, a simpler answer. You know what I'm saying? A simpler, complex. I mean, making it more simpler than as complex than saying that it's the 15 through 9 and then the 8 bits. Okay. To me, it just once I get into all that, it kind of confuses me a little bit.
Okay,
so I'm just trying to simplify it a little bit.
I want to say something that I'm seeing in chat and I'm hearing. To unconfuse this, I want to make sure that you understand that even what Oscar just said, I think would confuse Ebony in this one. It's like Spanish and English. You know, it's not, you can't interpret 16 as, you just can't, you know, because you write it out totally different. You know, it would be 1, 6, 1 and 6, but 1 and 6 is not 16. It's just 1 and 6. So I just want to make sure that that's clear.
It only goes
2 different languages.
0 to 15. That's your options. 0 to 15 because you only have 16 total places, and 0 takes up one of those places. A byte has 8 bits. That's 0 to 255 because 0 takes up one of the spaces. And we can only go as high as F. Ingrain that in your brain. If you see anything higher than F, it is invalid. It does not compute. It will not register. You will see questions like that, and they sneak it in there. What they will do is they will give you something like this, which all of that we just did is just for me leading into talking about this one slide. But it does come up again and again. Right here, this is what an address or a MAC address, which is called a media access control, which is kind of like a social security number for your network interface card. This is what uniquely identifies your network interface card. And it has 48 bits that they've broken down into these little chunks. So it has 6 little chunks. 6 times 8, 48, right? So it is 12 hexadecimal characters in 6 segments broken up by colons. If you see that, that should trigger your mind to saying that is a MAC address, and that is what is uniquely identifying my device, my network interface card on my computer. And computers can have more than one NIC. Like you have a wireless NIC, which is how you communicate with your Wi-Fi, and then you have a hardwire NIC, which is how you would communicate with a landline. It is broken up into 2 sections. So you have the first group of 3 and the second group of 3. This first group over here identifies the manufacturer who made it. The second 3 off to the right identifies your unique individual device. Are there duplicate MAC addresses out there? Yes. But it's also known as your hardware address. So it's your NIC card. This is its unique identifier, and certain devices on the network will use this to identify your unique computer. So here's the other names they use for it: hardware address, physical address, your adapter address, or your Ethernet address.
24.
Does this make sense? It's supposed to be globally unique, but supposed to in reality aren't necessarily the same thing. But for the purposes of this, no two have the same. Before you say it, Greg, we have not gotten to security yet. If you're talking, you're muted.
Oh no, just saying that, no, everything's great. I just want to make sure everybody's pacing, you know. I'm seeing people, you know, in chat and so forth. So I just want to make sure everybody's on the same page.
Are we making sense with this? So we use these MAC addresses, which is a combination of letters and numbers to create a unique identifier or social security number, kind of like for our network card, so that it can communicate with the network. Does that make sense? We call that the MAC address. If you look on your phone, if you look on your computer, if you go to the settings on your phone, it'll tell you what the MAC address is for your phone. And it will look exactly like this. 6 groups of 2 hexadecimal numbers using numbers and letters, making up a unique address. Are we good on this? MAC address, hexadecimal, identifies our NIC. We will come back and revisit MAC address again. Again, we're not expecting you to be an expert on this. This is your first exposure.
Actually, you know what? Oscar brought up something that I want to make sure that are we headed in that direction? Because I don't want to bring it up yet until you get there. But are we doing, because we're doing base 2, base 8, or octets? But are we doing base 10 at all in this at this junction?
No.
Okay, that's what I thought. Okay.
Yeah, we're not going to get into base 10. All right. Are we all okay right now? I'm not saying we got to be like, yeah, it's awesome, I got it, but just like it's making a little bit of sense. Oscar? Yeah. Golly. Yuki, thank you. Rebecca. Making a little bit of sense. Ebony, awesome. Jamari, nice. Danielle. Bernard, nice. Beautiful. Okay, again, we're not trying to be experts in this. We're just trying to get an understanding as to where this stuff is coming from.
Mr. Ken.
Yes.
I'm a little bit confused that it's saying the 48-bit expressed in a 12 hexadecimal, but the hexadecimal is 0 to 9 and A, B, C, D until F. So where's the 12 hexadecimal?
Hold on, I'll show you. So this here is what the computer sees. It's 48 bits. That would be the actual MAC address. What it's doing is breaking it down. So into little chunks. Like this. So it's breaking it down into chunks like this. And then each one of these chunks will be broken down into 2 nibbles. So when you see it, you're seeing nibble 1, nibble 2, colon to break it up so it's easier for you to read. Nibble 1, nibble 2, colon, so it's easier for you to read. So all the computer sees is this long string of numbers. But when they print it out so that you're reading it in this easier to read format, broken down into these hexadecimal characters broken up by the colons. Does that make sense? So that's what they mean when they're saying this. So there's 48 bits. So 48 ones or zeros. And they break it up into 12 little characters separated by these colons to make it easier to read. So that's essentially what they're doing. All right. I like the engagement. Any more questions? Okay. Now, shift gears a little bit. Now that we know that each network device has to have a MAC address, that's kind of its unique identifier on the network so that they kind of know how to route traffic to a degree. We're going to talk about different types of devices that we use on our networks. You've heard us mention a hub, a router, a switch, stuff like that. What are these devices? How do they work? What do we use them for? So the hub, probably one of the simplest devices on the network. Basically, it is a dumb device. It doesn't look at anything. It doesn't evaluate anything. All it does is it screams your business out to the entire world. So if I wanted to, have a private conversation with Rachel and I walk into this busy room and I just start shouting what I want to talk to her about, that's basically what the hub is doing. Every piece of information that goes into this hub gets blasted out to all the ports on the hub. And what's happening is the computers on their end is basically looking at the information as it's coming in and going, nope, that's not for me. And it ignores it. So this is where collisions can happen. So we're back to that collision detection. So if this computer and this computer both start talking at the same time, because the hub is trying to blast it out to everybody, it creates that data collision where everything gets garbled and nobody understands what's being said. So then they have to do that collision detection where they both back off, they stop for a minute, they roll the dice, get that random number, and they wait. And then whoever had the smaller number, they start talking first, and then communication can continue. That's kind of how a hub works. So it's not me privately messaging Rachel and saying something directly to her. It's me basically just shouting it out to everybody, but everybody else ignores it except Rachel. Each computer you add to a hub slows it down even further, because you're having more collisions. More people are trying to talk. Computers have to back off more often. So each time you add a computer, it gets slower and slower and slower and slower. So how do we combat this? What could we do to kind of simplify this? Well, we can move up to the next level device. These operate on what's called layer 1 of the OSI model. We'll talk about this on Monday. But these are what are called a layer 1 device. So we need to up our game a little bit. And that would be a switch. Now, what a switch does, instead of shouting your business out to everybody, it uses those MAC addresses we just talked about. So when in an unmanaged switch, which was, like as Greg called it, was a dumb switch. When you hook up a bunch of computers, they all kind of talk to the computer. Basically, like mine says, hey, I'm Kelly. Rachel's like, hey, I'm Rachel. And we're using these MAC addresses to identify ourselves. And if I want to have a private conversation with Rachel, I can now send a message directly to her via that MAC address. And so instead of sending it out to everyone, it sends it just to the port that Rachel's on.
Would be good for me.
There is data analytics?
Yeah.
Oh, or maybe it are. Maybe I'm wrong. It does have to. I'm pretty sure data entry has nothing.
So it's more of a direct communication. So there's no collision, right? It's just me communicating directly with Rachel. And then if Stephanie wants to talk to DW, she doesn't have to blast it out to everybody. She is communicating directly with his MAC address. So the switch is saying, as the communication is coming in, it's saying, I want to talk to this MAC address, and then it sends it straight to that port that MAC address is going out on, and there's no data collisions. So if you have a network full of hubs, the biggest thing you can do to increase performance is just replace hubs with switches. It cuts down on your collisions. Data moves a lot faster. But we are still able to communicate with everybody on that switch if we want, by doing what's called a broadcast. So if I want to communicate with everybody, I can do a broadcast and still shout out that message to everybody. So we would separate things into what are called collision domains and broadcast domains. On a hub, the entire hub is a collision domain, because if anybody talks, all that data can run into each other, right? Like we were talking about. So every piece of data you send over that hub can collide with another computer if they're trying to talk. The switch breaks up every single one of these ports on a switch. So this one has like what, 5? Each port is its own collision domain. But the whole thing is a broadcast domain. So I can still communicate to everybody if I want to, but I don't have to. And again, like I said, we will talk about this a little bit more on Monday when we get into TCP/IP and we talk about the OSI layers. The MAC address operates off of the second layer of the OSI model. So a switch is called a layer 2 device. Yes, they have layer 3s. but that is beyond the scope of A+. So a switch with regards to A+ is considered a layer 2 device. And even if I have this much, if I add more nodes to it, does not typically split the speed or slow the system down more. That's the beautiful part of a switch. They're real effective tools with regards to networks. We'll get into what a managed versus an unmanaged switch is later. Yes, Oscar.
So why would you even use a hub? Like, it's just like cost reasons, or?
Well, typically hubs would be used currently still as they're just kind of, they haven't been phased out yet.
Correct.
It's one of those things where it's still, they're still out there rarely, but that's one of the quickest ways you can upgrade a network. If you come across a hub, you can just switch it out for a switch. You do nothing else, you will drastically improve the speed of that network.
Big time. I have a story about that, man. It was really bad. Yeah, but yeah, same thing.
So yes, but would people typically opt for a hub? No, not usually nowadays. But are there still hubs out there? Yes.
And if you work with a company, well, I just give you a little piece of what happened to me. But one of the main devices is this one business. In the server room, they had a hub coming out of the server room to connect to switches. So all the offices,
kidding me?
Yes, they never upgraded the stuff that was in the right in the closet
rack?
behind the server. Yeah, exactly. Behind the server room, there's a hub to get it up to the other floors, and they never switched that out. But they switched out all these brand new spanking, switches on every level. I was like, it's not improving. It's not improving. And eventually we reversed. Just looked at all the connections, and we saw this one hub in the closet, and that was the problem.
Wow. But yeah, that can happen. Did you have another question, Oscar, or does that make sense? All right. All right, so we're okay on hubs. Hubs are layer 1. They shout your business out to everybody. Don't care who's listening, they just shout it out to the world. The switch, layer 2, with the fun use of MAC addresses, now we can uniquely identify who we want to communicate with on our network. And I can send messages directly to Rachel or directly to DW, and everybody doesn't need to know my business. So it allows for that one-to-one communication. Next. Bridges. Bridges, this one always confused me because I always had trouble with bridges and routers. Bridges connect between two physically different or dissimilar networks. So if I'm translating over coaxial cable or like cable internet, if I'm coming in with coaxial, but everybody else on the network is operating on Ethernet, I need a bridge to translate between the coaxial to the Ethernet. Or if I'm going from fiber optic to wireless, if I'm changing over what media I am using, I need a bridge to make that happen. So if I have a wired LAN and I want to add on a wireless mesh network for the employees to use as well, I need a bridge to connect that wireless network to my wired LAN. So that is what a bridge does. Two physically dissimilar networks connects them together so that they can communicate. Yes, Kali.
So it's like, so would a like a access point, those mesh point, when you connect it to your, I guess, router, would that be the bridge to like mesh the other, like let's say in your your house type of thing? Would that be the bridge or no? Like this?
Yeah, well, okay. The misnomer usually is and this is where terminology gets to be a problem. The device that's in our house, everybody calls them routers, but they are essentially an all-in-one device. They do a whole bunch of different functions, but yes, they do have a bridging technology in there where they will take that cable internet and change it to wireless so that we can use it.
Oh, okay.
When we get to network, Soho networks, we'll talk a little bit more about that house router. And it's like it's a hub, it's a switch, it's a router, it's a bridge, it's a wireless, it's everything in one. So it's, you know, it's kind of all those things together. All right, a gateway. Now, gateways are used, so bridges connect to physically different networks together. A gateway will connect to logically dissimilar networks together. So token ring over to Ethernet, or a LAN to a WAN. So these are logically different. We have a star, we're moving to a bus. You know, we are using logically different networks. You're connecting those logically different networks together. Does that make sense? So bridges connect physically different, gateways connect logically different.
Mr. Kelly, what was the slide before this one?
Well, we're on slide 22, so it was 21.
Right, can I see it real quick?
Sure. There you go.
Okay, thank you. I've been taking pictures, and I had to use the restroom real quick. I missed like 3 minutes.
No
Thank
worries.
you.
All right. So bridge and gateway, physically different versus logically different. Gateways also can connect us to our outer networks. Routers. These are layer 3 devices. They route based off of IP addresses, which is, we need IP addresses if we're going to communicate out onto the World Wide Web or internet. We use MACs typically to communicate on our networks, IPs off our networks. What it does is the router moves things like packets of information between subnetworks. So like it'll send it to a router next to it, that router send it to another router, that router send it to another router, and it will map its way to its destination. But this is happening again in milliseconds. And usually they have routing tables already on them that tell them who to communicate with depending on where the packets are going. Many home routers will use what is called a DSL, or excuse me, will share cable or DSL, and will allow wireless all on one piece. And that is, again, that all in one device. But this is how you would connect from your internal network to an external network, your intranet to your internet. Questions? The other pieces prior to this, with the exception of the gateway, because the gateway can connect you to the outside, but your bridge, your hub, and your switch all operate on your intranet. That's your internal network. The routers get you out into the scary world of the World Wide Web. Questions? No? All right. Other devices, which we will get into a little bit more later. Yes, Kevin.
So like, just to, I'm a little bit confused with the whole, so like routers they go out into the, you know, they get from the internet, like the wireless, like web or whatever.
They can, yeah. Routers and gateways can be the same thing. But what it is, it's connecting two networks together. So if I was connecting, you know, my internal network to the outside World Wide Web, I can do that. But if I had different networks inside the company, I can use routers to connect my you know, like operations to accounting.
Okay, and they're replaceable, like they're interchangeable with switches and hubs, or
no. Routers sit on the edges of your networks.
Okay.
Switches and hubs are usually in the middle. So if I'm talking within, like if I'm talking to our class, they would say like, you know, Zoom is our switch. So we're all talking together, right? But if we wanted to go talk to Avery's class, another class, I would need to go through a router to talk to that class to be in that network.
Okay. All right. That makes a lot more sense to me now. Okay.
Any questions? All right.
I'm sorry, before you go on, so with that comparison with the bridges is still like something you would use inside of this class, like you know, to communicate between this Zoom call, or?
Well, the bridge would be probably your router or your network device at your house. You're going from a wireless connection of your computer to that, and then the bridge would translate that wireless signal into a wired communication to go out of your network. So the bridge translates two different types of media.
So
Firewire, or excuse me, not firewire, but fiber optic, like using light, to using Ethernet, or, you know, the phone cables. So you're changing the type of communication media you're using. The bridge, you know, overcomes that gap. So wireless to wired, fiber optic to Ethernet, you know, whenever you're changing the media you're transmitting on, you need a bridge to be able to do that.
Okay, so the bridge, would it be able to kind of do the same thing like the router, like go outside of the network?
No, that would be different. You know, the bridge could change. Okay, so the bridge could change it like from a wireless to a wired communication. And then the bridge would send the signal to the router. The router would change it from internal to external.
Okay, okay, got it.
Make a little more sense?
Yes, thank you.
Okay.
Can you explain about the firewall again? Sorry.
I haven't gotten to the firewalls yet.
Okay.
I haven't even started the firewalls yet. Sorry.
Okay, I thought I missed it.
No. We're gonna do a brief introduction on firewalls here. Firewalls is a security appliance. It's protecting your networks. We're not really going to get into the packet filtering versus stateful. We'll deal with that in a later presentation. Essentially, a firewall uses a particular set of rules called an access control list to determine what kind of communication can pass between you and what's on the other side of that firewall. Typically, they're kind of set up as passive, where communication can't initiate from the outside. So like, you know, if Courtney tried to call into the class or send a message into the class, it would not allow it. But if I sent a message to Courtney and said, hey, can you please send me information on this? And then she could send the information to me. The communication has to start from inside. The firewall is just kind of trying to protect you. It is a barrier between you and what's on the other side of that firewall. Usually it's the outside internet, so that people can't just barrage into your networks and wreak havoc. So it's basically a security device. They can either be software based, which is like the Windows Defender firewall that we talked about the last week, or they can actually be a hardware, like an actual physical piece of equipment that you would plug in two cables, your internal and your external, and then all communication would have to pass through the firewall and it would do its thing. So it can be hardware or software. It uses a particular set of rules like we talked about called ACL, or Access Control List. Does that make sense? It's just used to protect your network, to make sure people can't talk if they're not allowed to. Yes, TW.
What is the biggest benefit from having a physical firewall as opposed to a software firewall, or a device that integrates the firewall with another network device, like a router and firewall?
They tend to be more robust, more powerful, have more computing power. So if you're doing things like packet filtering, it's able to read through those packets, and a single device can protect multiple computers versus a software firewall protects just the one machine. So it wouldn't just protect your computer, it would protect your printers, it would protect your thermometers, it would protect your Ring cameras, all that stuff would be protected through a hardware firewall. Greg?
Hey, all right. So I had somewhat of a question. I guess it must be an A+ question. So when dealing with bridges, and you said something about not being clear on it all the time, because there is a nuance there, right? For example, if you are given like web servers to host, like in-house web servers to host, and you know what, I shouldn't even use that. But you want to be able to operate on a DMZ, or you want to be able to have all external IP addresses on your internal network. Let's just say that you use bridge mode for that purpose. Would this not be considered? Are they two different terminologies as it concerned with A+?
That would not be, I mean, that's kind of a question. We can talk about bridge mode and stuff when we get to Soho routers.
Okay, all right, sounds good.
So please, yeah, put a pin in that for now. We will, we'll come back to that one.
Thank you.
Mm-hmm. Kevin.
Yeah, so like, I don't think we talked about them, but like, is there like, so I know there's routers and there's modems. Like
a modem is a very specific thing. It means modulator, demodulator. And a modem is specifically meant for like old school POTS lines where you would have the audio phone line coming in. And what it would do is it would translate an audio signal into a digital medium. And then
so that's strictly for dial-up then, like is what a modem. Okay. So like, so because I know like everyone, and that's probably like, because like my father and like everyone like calls the thing that for Wi-Fi in my house right now is like they call it a modem.
Yeah,
but it's not,
or a router or whatever. And
a router, yeah.
And it's one of those things like that's where like the colloquial terms versus the specific technical terms we need to use get blurred, and we need to understand that, especially when we're dealing with customers. Understanding that they may not use the proper technical term, but we understand what they're talking about. But when we're communicating with each other, we need to use the proper technical terms.
Okay, yeah, because that's what was just that was like the last thing that confused me. I was like, wait a minute, that sounds just like what that does, but I've been calling it a modem for so long.
Yes.
That so
well, it's like the difference between storage and memory.
Exactly, yeah.
So and I still do that today. Like if I'm just talking, I'm not paying attention, I will mix up the two.
All right, thank you.
Rebecca.
I'm still confused with the firewall. Is it a software or is it a kind of hardware thing?
It can be both.
Oh.
So there is a software version, which is like a piece of software you would download onto your computer. Like Windows Defender Firewall is a good example of a software firewall. So that is a piece of software on your computer with Windows that operates like a firewall, but it protects a single device.
Okay, it can protect only one computer at a time.
Yes.
Okay.
And there might be a hardware firewall, which may literally be like a physical box. And then you would plug in your network cable on one side and then plug in have the other one come out and talk to your network on the other. And it is a physical box that does the firewall actions for you, but it protects everything on the other side of it.
Okay, so is it connected to the router?
Yes. Mm-hmm. So you would have it say in between your router and your network. So like you have the cloud right here. That would represent the internet, and then your line comes in, and then you would have like your router maybe, and then you would come in, and then you'd have another device here, which is your firewall. There we go. And then come in, and then you would have your internal network in here. So anything inside has to pass through the firewall to get out to the network. Anything from the network comes into our router and then has to pass through the firewall to get to us. If it's not supposed to be there, firewall stops it.
It stops it. So basically it's protected.
Yes, it is
That's what
one
it is.
aspect of security to protect your network.
Thank you.
As far as stateful and stateless, we'll get into that a little bit later. Yes, TW.
Yeah, you know, tend to be, well, some of the good ones are very, very expensive, right? So, in a cost-minded company, what ways would they like try to implement to install like a firewall device without spending so much money? Would you be able to set up maybe a router and configure it strictly to do firewall, or like a computer, not a router, sorry, a server or and configure it specifically for that purpose with some you know, firewall software?
Likely you wouldn't do that. I mean, I imagine you could, but if you were cost minded, you might use a UTM or a unified threat management device, which kind of gives you an all-in-one package, and use that with Azure Firewall.
Yeah, that's.
But we'll talk about that when we get to security, though. But that's a great question. Any others? Right.
Wait.
Yo.
So like, would an antivirus program be kind of like a fire? Would it just include a firewall or something?
Well, you might have an anti-malware suite on your computer, which is a combination of programs. Antivirus is a very, very specific thing. You know, combating and getting rid of viruses, but malware encompasses a very large variety of things. So no, anti-spyware would not be considered a firewall, but you might have an anti-malware suite that included a software firewall in it. Again, Windows Defender Firewall has that built in that anti-malware suite that they give you for the operating system.
All right.
But they are separate things. Okay. Now we can dial it back to getting into some simpler things. Just talking about pure hardware now, just cables, you know, it just gets so much simpler from now on. Good news is we've crossed the halfway point of this technical session.
I was gonna say, isn't it time for lunch? You gonna start this one now?
Bad news is Oscar's about to cry. Why don't we go ahead and put a pin in it right here before we jump into a new subject? Everybody's a little continuing on our introduction to networking journey. Coaxial cable, exciting stuff. So coaxial cable, as you can see, broken down into its core components. You have your central conductor, which is that copper wire in the middle. That is what transmits the data. This fun dielectric core is just a fancy name for a piece of plastic that keeps that little copper wire in the middle of the wire. So it holds its place and it kind of protects it as well. Outside of that,
Can you drop the link, please?
I absolutely can. Outside of the dielectric core right here, this little white piece, you have this kind of mesh, which is a braided shield. This helps protect from EMI or EFI. So, yeah, electromagnetic or electrostatic shock. So it helps protect it, doesn't make it completely immune, but it helps protect it from that. And then you have the jacket, which is that PVC coating, which goes over the outside of that cable itself. There are 3 types we need to be aware of. You do not need to know the ohms. Don't worry about this. So, RG6 is typically used by the cable companies to connect your homes to the cable company. So this is the exterior portion of the cable that runs along the telephone poles and all that stuff. That is your RG6. It is a thicker gauge. When you're talking about wires, the lower the number, the thicker the cable is. Same things goes with like piercings and stuff like that. The thicker or the smaller the gauge number, the thicker the cable. Inside, we will use an RG58 or an RG59. Typically for short distance, you will use the 58. Longer distance, you can use the 59. And I believe the 59 is more data oriented, 58 is more cable TV, things like that. So this would be legacy. So it is the older technology. 59 is typically what we're using for the most part today.
Which is
What?
important to remember.
Yeah.
That the RG6 is outside to the home.
Yep.
Right? And inside is the RG58 or 59. And I just found out that RG stands for radio guide.
There we go.
From the military. That's
Radio
just
guide.
interesting to know, you know.
A lot of this stuff comes from somewhere. So interior 58 and 59, exterior 6 for coax. Two different types of connectors on the end of that coaxial cable. You have your BNC, which we talked about this morning, which is this one here, bayonet Neil Councilman. It has the male piece has a T on it, it slides in, and then it twists and locks in place. It allows for quick disconnect and connects. This is typically used for networks and offices and things like that. This is typically where you would see it, where things would be disconnected and reconnected, you know, on a regular basis. So they want the ability to quickly disconnect or connect. Versus the F connector right here, which is what you would typically see in your house with regards to like cable and like your cable internet and stuff like that when it comes in the house. Because typically when that is being put on, it's like a threaded screw. It is threaded on and then is left alone. It's typically not something you're going to be moving on a regular basis. So in your house, you would see the F-type connector right here. In offices, you would see the BNC connector. So those are the two different connections you can have on a coaxial cable. Good. Are people leaving or coming in? Scared to ask. All right. Now we can put coaxial cable behind us and we can move on to twisted pair cabling. They start out with the STP, as you heard mentioned this morning, which stands for shielded twisted pair. Twisted pair basically means they take two wires and they wind them together, twisting them together. You will have typically a solid with a striped of the same color, twisted together. Why they do this is when they are twisted like this, each cable is only ever touching the other at a right angle. And this allows for the data to travel a longer distance without what's called crosstalk. If they're laid parallel with each other, the signals can actually jump from wire to wire, causing crosstalk, which can degrade your signal. So the whole reason they twist it is so that they can run that signal further without the signal degrading. It's called attenuation, where the signal starts to break down. You remember us talking about certain cables can only be specific lengths? Like they can't go longer than that. This is why, because the signal can jump from cable to cable over time, breaking down that signal. And then again, they twist it in order to prevent that. And then they put this fun little tin foil in right here, which helps shield it from outside electromagnetic interference. And some of you may see this extra piece here. All that is a piece of Kevlar string or thread to kind of give strength to the cable. So that's all this extra piece is down here. The main meat of it are these 4 sets of twisted pairs. Questions so far on this? So shielded means it has this extra bit of tin foil on it to protect it. That's all it is. The difference between STP and UTP is this tin foil. All right. Here we go. UTP, unshielded twisted pair. Looks exactly the same, right? You got the 4 sets of twisted wires, but we don't have the tin foil, right? So you can see it, we get up here, there is no shielding. You still have that PVC coating, but it's just the 4 twisted wires in here. Overall, this tends to be your most commonly used in networks because it is the least expensive. No additional materials needed. It's easier to work with. And not every location is going to need that shielding from interference. So that is the difference. Shielded, tin foil, unshielded, no foil. So here's some categories for internet. And you're asking yourself, good gravy, do we have to know this? To a point, yes. Mostly you need to know your data rate and your cable length. Cable length is pretty much the same across the board. It is 100 meters. Or 300 feet. So that pretty much doesn't change when you're talking about twisted pair cabling. But you do need to know your speeds. 10 megabits, 16 megabits, 100. Cat 5e gets you up to the 1 gigabit mark, which is nice. 6 and 6e gives us 10. And then 7 gives us 10, but it is also has built-in shielding.
What's the difference between Cat 6 and Cat 6e? They look like they do the same thing.
6A, excuse me, 6 and 6A. I think A. So what it was 6 would give you 10 gigabits up to 55 meters, and then it would drop down to like 1 gig after 55 meters. So it didn't allow you the full length at 10 gigabits per second. So you could still use it up to 100 meters, but you would see a drop off in speed. Cat 5.6a, which is augmented, allows for full 10 gigabit speed, the entire 100 meters.
Okay.
I would take a screenshot of this just to have it for your notes.
So does Cat 7 give you the whole 10 gigabit, the whole 100 meters too?
Yes, for 100 meters, and it also employs shielding as well.
You said they have shielding?
Yes. So shielding is standard on 7, where it's an option on 6 and below.
Okay.
Thank you for the Google search, Oscar.
I missed that. Which one has shielding?
Cat 7 shielding is standard as opposed to optional.
Okay, yeah. I'm glad I asked. No, thank you.
All right, we all have pictures of this. Yes, Oscar, I see your hand up.
So if you plug in, let's say someone has like gigabit internet or whatever, it's supposed to have a gigabit internet connection, and they're not getting that speed, like they're getting 100. I mean, it can trace back to the cable, like it'll just be like,
oh, you absolutely can trace it back to the cable.
Okay.
The cables are one of the most common offenders for bottlenecks, and people don't realize it because they think a cable is a cable is a cable, right?
Okay.
Yeah. And bosses don't ever get that too.
If you walk into a Cat 6 network, like you have a Cat 6A network, everything's pretty, 10 gigabit speeds, everything's running nice, and you plug a Cat 5 cable into that switch, you can bring an entire network to its knees.
Wow.
By using one wrong cable.
Mm.
You have to be very cautious about the cables you're using when you're introducing them into networks.
Gotcha.
Thankfully, on the Ethernet cables, though, typically stamped on the sides, I don't have one handy, but typically stamped on the sides of them, if I have it. I'll have to bring one in when we do TCP/IP on Monday. But on the sides of it, they have the standards stamped on the side so you can quickly see what it is. So when we do TCP/IP on Monday, I'll bring a network cable so you can kind of see it written along the sides of it. So yes, you do need to be cautious about that. The other thing you need to be cautious about is how you have them wired. Like if you introduce a crossover where you need a patch cable, you can cause other problems. So cables are very, very important and often overlooked in the troubleshooting process. So excellent question, Oscar.
Thank God for port sense.
Right, yes. So on twisted pair cablings, we have two different types of connectors that we had gone over earlier. We have the old school POTS connector right here, which has 2 to 4 pins. It is, yes, a twisted pair. And it is called the RJ11, which is the square connector. It is the squarish looking connector. And over to the modern Ethernet type cable, more rectangular, and has 8 pins for connection, and that is the RJ45. So that is the name for our connector, RJ45 versus an RJ11. See, we're cruising now. We're already up to slide 30. Questions so far? All right. Wiring standards. Do we need to know the order that the wires are put in inside that, RJ45 connector? Yes, yes, we do. And what you're probably thinking.
Do we need to know A? Do we really need to know A?
Yes.
Crap.
I know the majority of the industry uses B, but yeah, you still got to know A.
That's what told me off. Okay.
But you're asking yourself, do you please have some kind of method where we can remember this stuff? Yes, we do. We have a mnemonic so that we can, kind of break this stuff down and remember it a little bit easier. And these are the T568A and B standards. So Greg was just mentioning, the majority of people use this one, partially because the mnemonic to remember it is significantly easier. Sun to the sky, brown to the ground, and the river runs between the trees or between the valley. So your oranges go up top, your browns go down in the bottom, and then the blue runs in between the green.
I never knew that, but I just always memorized it. It was like orange, white, orange, green, white, blue, blue, white, green.
Yeah. So it's, sun to the sky, orange to the sky, brown to the ground. Brown always goes to the ground, and then the river runs, you know, through the valley. So the river between the greens. Always remember, it starts with a stripe. So it goes stripe, solid, stripe, solid, stripe, solid, stripe, solid, stripe, solid, all the way through. Only 4 wires change. Your blues and your browns never move. So no matter which way you're doing it, blue and brown never moves at this time. They have modern crossover cables and stuff that use all 8 wires. It's a little different. We're not worried about that with A+. That's 1101, not 1001. 1001, blues and browns never move. Stay the same all the time. So it'd be orange stripe, orange. And then you go green stripe. And then it's solid blue, blue stripe, blue, green, brown stripe, brown. So remember, stripe solid, stripe solid, stripe solid, stripe solid. Always alternates. So pins 1, 2, 3, and 6 are the only pins that move. Let me go to A. This one never makes sense to me. I just remember that green and orange are the only ones that change. So it's like trees to the sky, and the I don't know. The mnemonic is a little bit later. Sorry, I can't remember. I can never remember this one. I remember the first one because it makes sense, and then the second one I know it's the orange and green switch. So yeah, the only differences are wires 1, 2, 3, and 6. Blue and brown stay the same. Take a picture of this one, please. And it's T568.
I think it's trees to the sky and the river runs on a sunny day, and brown is ground.
Okay, trees to the sky, brown to the ground, and the river runs on a sunny day.
Yeah.
Okay, thank you.
I think.
Makes sense. Makes sense.
Yeah. B is the most common, and that's the sun to the sky. So everybody got a picture of this?
Got a question.
Yeah, I got it. What's going on?
So like, do they like have the number on them? Like, you know which side to start with, or
well,
like,
what this is if you're looking at the back of it, see that this little tab thing here? That's the little click, the little tab that clicks when you plug it in. This is looking at the bottom of that. So the tab would be away from us.
Okay. So that's what I'm saying. So how would you know where, if you start, if like, so right now, the way you're looking at this picture, left is 1 and then the right side is 8. So I guess like.
If you were looking at the bottom, okay. So see this little tab here?
Yeah.
So that would be facing away from us.
Okay. So,
if we're looking at it here, that is facing away from us. And then the top one would be orange, and the bottom one would be brown.
Okay, I got it.
Does that make sense?
Yeah.
Okay.
Yeah, if you had it in front of you, it would make a lot more sense because
yeah, I mean, if you have
pins.
one, if you have one laying around, like you use one for your computer, obviously don't unplug your computer. But if you have one laying around, please take a look at it. They usually use clear connectors, and you can look at it and see the patterns that they use.
Yeah, and if you try to do it upside down, you just can't make it out. So it would make sense when you're putting it together. If you're making it, it would make a lot more sense.
Yeah.
Okay.
So there's that. And here's the mnemonics for it. So 568A, trees to the sky, brown to the ground, and the river runs on a sunny day. So the green to the top, brown to the ground, and then the river runs between the orange. T568B, sun to the sky, the orange, brown to the ground, and the river runs between the valley. And the odds are striped. Thank you, Oscar. Evens are solid, odds are striped. That's pretty cool, Stephanie. And now if I have a bad cable, since I learned how to do it, is I usually just cut off the connector and remake one and see if that fixes it, because sometimes it's just the connector going bad or getting yanked and damaging the wire. So excellent. All right, moving right along. Plenum cable. Oh my goodness, do we need another type of cable? So plenum wraps each individual twisted pair in its own set of foil. Now, the nice thing about plenum is the jacket itself. See, normal Ethernet cables are wrapped in what's called PVC, which is polyvinyl carbonate or something like that. No, polyvinyl chloride. So when it burns, it releases chlorine gas, which is not so good for humans. Can make us very sick and or can be fatal. So they have one that is actually resistant to burning and does not release poisonous gas, and that is called plenum cable. This is typically run through HVAC systems, air conditioning on buildings. They run it in drop ceilings in offices, above those little tiles that hang down or whatever. They'll run it across there. Anywhere where it would be in the airflow of people, they would typically use plenum. If fire and Ethernet cable is ever mentioned in a question, your answer is plenum. If it's going in an air conditioning vent or a drop ceiling, your answer is plenum. Will you see a question on this? You will see multiple questions on this. So it's fire resistant and it goes where humans would, like where airflow would be. Drop ceilings, HVAC, plenum. Please, please commit that to memory. I promise you will be asked about it again and again and again and again. All right. Questions on plenum? Kevin, where do we use it? Uh-oh. Rahel, where do we use plenum cable?
Air conditioning?
Like in HVAC systems? Where else?